Do some refresher from last week, but we're building, and again, I'm going to do the exact same thing I did last week. I'm not going to keep you until 10. I'm going to let you go a little bit early. Main thing, I want to get the key concepts to you. Now, immediately after this lecture today, I'm going to be meeting with someone to do a power calculation for them. I've often joked, the only reason people keep me on this campus is I can write that power calculation. They do not keep me around for the sake of my personality. They want me to write power calculations. But this comes back to the idea. Remember what I told you last week? I told you the truth, the harsh truth, that modern statistical textbooks take two very different approaches and put them together, smash them together, and hide that fact from you. Last week, I talked to you about p-values because they are prevalent everywhere. And I wanted to make certain you could understand the correct interpretation of a p-value. That was really what I wanted you to get to understand. It's a probability. It is not a probability of truth. It is not the probability of anything to do with the hypothesis. It's the probability of of observing that data under a set of assumptions. Okay? That's the key thing. It is the probability of observing a set of data or an outcome, or one more extreme, under the belief the null hypothesis is true. It's always about your evidence. This week, I pushed well beyond that, and now I have to jump into power, which is the other person's approach. P-value was Fisher's. We're going to go over to Nathan Pearson's approach. And this is why people get so confused with, I don't understand power. Because power, you never discuss power and p-values at the same time. No reason. They came from two different camps. But it's important to know what power is. What is power? What do you think power is? What is statistical power? And why do we care?
The ability to distinguish if there is like a difference, if one truly exists.
Right. Now notice what was just stated. There is what was just stated is a conditional statement. Given one exists. Remember how I said the p-value, the probability of observing the test statistic or one extreme given the null hypothesis is true? What was just stated is, what's the probability of observing a significant effect, a statistically significant effect, given the alternative? Given the alternative hypothesis, not the null hypothesis, is the same approach, but now you've got to expand the assumptions. Okay? So, we're going to go through, and this, I actually am in a bad mood. It's not your fault, I promise, and it's not 280's fault. It's actually my consult fault that's going to come up in about an hour and a half. We're going to do what I have to typically do. Let's talk about two group comparisons, because that's the easiest way to start coming in. Okay? Then we're going to talk about doing examples for two group proportions. How do we do power? And then I want to tell you why, and again, I'm only trying to get you the beginning of it. I could do power for regression. I can do power for ANOVA. Just trying to get the foundation. If you get this foundation, you can talk to any methodologist correctly about power and get it done efficiently. The consult coming at 9:30 will not be efficient, I guarantee it. Okay? It's just not going to be efficient. And then I'm going to point out something. This is over and over. This is where the mistake has been made. They're coming to me. The grant goes in 4 days from now. 4 days. And they're screaming, I need a power calculation. Well, actually, you needed a lot more than that. Because the power is not the most important part. It's actually not the power itself, not the calculation. You'll understand that in a minute. What is statistical power? I give you two definitions. And this is the truth. I have situations where even members of study section forget this. It is simply a description. I'm describing a forest to you. I'm describing a landscape, really a mathematical landscape of the possible experimental outcomes for which we are likely to declare that the intervention or experiment that you designed actually had its intended impact, period. Okay, that's all I'm doing. I am saying, under these conditions, you have a good shot. If this is the weather on this day, you might want to go hike. You'll have a good day. If you want to go hiking, this is a good day to go hiking. But let me tell you, the forecast says it's going to rain. So you might not want to do that. It's nothing more than a weather forecast, folks. Under these conditions, we will have a good opportunity. If these conditions do not exist, we will not have a good opportunity. So, but I want to know, it's a description of possible likely to declare, or it can be written as a description of the sample sizes. What I'm trying to indicate to you is some people come to me and say, David, please sit down with me and work out the sample size for this experiment that I'm going to need. To which I'll say, let's get a cup of coffee. Let's talk. Tell me what your outcomes are. Tell me how many groups you're going to have. Tell me what a clinically relevant difference is. Notice I did not say statistically relevant. I did not say statistically significant. I said clinically relevant difference between groups. Tell me what matters. What's the smallest effect that you really give a darn about? Dean told me I gotta stop cussing in class. What's the smallest effect that you really give a darn about? Then we'll start building it out. But not everybody has that luxury to come to me and say that. Some people actually come to me and say, David, our budget says we can only get to 50 people. That does not mean we do not continue to discuss power. At that point, one of the pieces of the puzzle has been constrained. That does not mean there aren't other pieces of the puzzle I need to look at. Because if you come to me and say, I've got only 50, then I can still say, well, given you only have 50, you need to tell me, or you need to at least think about what type of conditions would produce this type of effect. Because that's the effect that would map to adequate power. All right, we're going to go through all of those. But you just need to sit down and discuss it. And remember, you know what a swag is? And I'm not talking about jogging, I'm not talking about running, I'm not talking about the swag bag of all the free stuff. You know what a swag really is? Power calculation is a swag. It is a scientific wild-ass guess. That's all it is. That's all it is. If my power calculation is known to be correct, I should be placed in federal prison because I am committing fraud. I already know the answer, and I charged the federal government an experiment when we already knew what was going on. It is not the first thing to be worried about in any experiment. Yes, ma'am?
So, I've always been confused by statistical power. And so you just kind of confirmed something I've always thought, which is that it's a guess.
It's a guess.
And so why has NIH then kind of glommed onto it so much so that you have these, people coming to you saying, look, I have this grant, that's a great idea, I think it's gonna revolutionize, whatever, but I need you to just sit down with me for 30 minutes and I don't care about it and do this power calculation for me?
Well, because the power calculation in and of itself, it is a guess, but it's an informed guess. It's a little bit of an exaggeration for me to call it a swag. I do sit down and I do rely on your clinical expertise. You know what realistic changes could be expected. I understand the concept of variance. I understand the concept of hypothesis testing and what's really going on in a power calculation. So what we're trying to do is we're trying to propose a reasonable experiment. Reasonable in two ways. We're not overshooting, we're not wasting resources, and we are getting to the level where if that is there, then mathematically we should find it.
But it's all coming back to this like idea of p-values, right? Like if
Yes,
that difference, like we say difference, when we say difference, everyone means 0.05.
No, that's not what I mean by difference. What I mean by difference is I have two chemotherapies. I sit down with you and you say to me, David, we're studying this, we're studying glioblastoma. The median survival after diagnosis is 18 months. That's standard treatment. We're proposing a new treatment. I have to sit with you and say to you, if the old approach produces a median of 18-month survival, is it worthwhile to produce a drug that moves that to 19 months? That's the difference I'm talking about. I'm not talking about 0.05s. I'm not talking about type 1 errors. I'm talking about clinically relevant. David, I'm going to give you a Lipitor. It's going to lower your LDL, we believe, on average by 3 units. Is it worth it? What magnitude must there be for you to say this avenue of research should continue? That's the delta I'm looking for. Okay?
But like in the situation you described, right, with glioblastoma, if we're going from a median survival of 18 months to a median survival of 19 months, you know, I would be like, okay, yeah, every day matters, right? But don't you then have to have this like kind of incredibly large sample size to detect a really, really small
That's
effect?
where we're going to get there. That's why we sit over that cup of coffee to talk about what are the different magnitudes and what is achievable. There's no need for me to propose a clinical trial that can never meet its approval. Let me go ahead. We're going to answer all these questions. You're thinking you could pretty much do the lecture. Let's go. Okay? It's not the first thing to be worried about. It's actually the third thing. At best, it's the third thing to be worried about. I mean, honestly, when you come to talk to me about designing an experiment, don't walk in and say, hey, I need a power calculation. Come in and say, this is what I'm measuring. These are the number of groups I have. At that point, I'll start asking, okay, now I have an idea of what avenue mathematically we need to go down. Now, start educating me about the biology. Talk to me about the literature and the effects that other people are looking for. That's where I start. And I don't give you one paragraph, I give you a grid. I'll come back in about a week, and here's your grid that describes the landscape. That's where NIH goes wrong. They want one paragraph. No. In my grants, you see the landscape. It's not a guarantee of success. People say, oh, I've got 80% power. You know what that literally means? No. We did this, we were able to do the experiment 5 times. And that effect exists 4 times. I did. 1 time, I'm going to flat out miss it. I'm not going to declare it statistically significant. It's there, but I make an error. False judgment. Please remember, it's not an exact measurement. In some ways, it's a guess about the future. It's very much a guess. You may say, David, I believe we can create a 25 unit difference between the 2 groups. That's what you believe. Okay? May or may not. What happens if you hit 18? Well, you design an experiment where you've got a little bit of slack.
so that if your assumptions are slightly off, we're okay. All right? Please understand, you must first define the specific aims of the hypotheses. Now I'm going to show you the truth about power so that when you get ready to meet with someone, I'm going to tell you this, you're getting a level that no undergraduate ever gets, no first-year biostatistician in graduate school gets. This is kind of like you just finished your comps. Now let's talk about what's really going on so that you're ready to do this. It cannot start anywhere else. I cannot, today, that consult that's coming, I've looked at it. I have no idea what that aim is. I don't even have any clue why you need a statistician for that aim. Really don't. So I've got a lot of education in front of me. Think of how you will measure the outcomes. What do I mean by that? It's the yes, no. It's yes, no, presence, absence. That tells me one thing immediately. It tells me I'm going toward a chi-square. Okay, I'm going to have to write my analysis plan that says chi-square, and my power calculation better align with that analysis plan, or else you're not doing good science. Think, and this is the thing, of what observed changes and associations would convince you that your research hypothesis is true. You should revise that slide. First one that would convince you. Then ask yourself which ones would convince your colleagues. Because guess what? You don't get to review your own grants. You don't get to review your own paper. Your colleagues do that. Okay? Immediately after doing those things, and it doesn't have to be carved or chiseled in stone. Don't feel like you can't come back and modify these things. But as soon as you've got it fleshed out, find a methodologist. I should change that, a statistician or a methodologist. Just sit down with us. Come to the bird clinic. Ask for some of the office hours. When are the office hours? When can I meet with him? When he's going to be sitting there at that kitchen table back there? Let's work it out, okay? All right, let's do an example here, okay? First, there are two hypotheses. There's the null and the alternative, right? This is what people do not recognize, okay? When we go start doing, we're in that framework that we talked about last week, the 4 steps. State the hypotheses, get your test statistic, then calculate your p-value or your rejection region. We're going to focus on rejection region this week. State your conclusion. All right. I literally have to imagine, believe it or not, I have to have an imagination. Under the null, we can say we're going to do let's just say for right now we're playing with BMIs, okay? And we're going to randomize people to 2 diets, and at the end of the study, since we've randomized it, everything should be balanced at the very beginning. We're going to look at the post, and we're going to say, is there a difference between the 2 diets? And I have to hypothesize and predict where those mean BMIs are going to fall. Under the null, I have to say mu1 is equal to some value, mu2 has to be the exact same value. Has to be, because the null would have to be true. I've got to write or imagine scenarios where that statement is true. And then here, under the alternative, this is your research hypothesis. And this is equivalent to someone a nutritionist sitting down to me and saying, David, at the end of this 6-week period, if there is a 2.5 unit difference in BMI, I think that is going to be clinically relevant. That's literally what that is saying. Now, this is a key part of our calculation. The ability to imagine a situation that could occur under the alternative that you would want to detect. Now, I have a question for you. Is that the only mathematical way I could make that statement? All right, tell me some other ones. Imagine with me. Give me some other ones. No, let's go ahead. Be prepared. We're going to come back to the imagination point. This is what statisticians literally do, okay? Are you ready for the mind-blowing, this concept you've never understood is this freaking easy? Okay? Under the null, this is the null. This is the null. The top one's the null. I put cut points down. And beyond the cut points, I reserve a certain percent of probability for type 1 error. I have put, literally, I have found my cut points that allow me, if the null is true, there's only a 5% chance that I'm going to reject it. But there's an alternate distribution. And there's no accident that I called it the alternate. That's the alternative hypothesis. What distribution would exist if the alternative is true? Well, if the alternative is true, it lines up at a different spot. And literally the probability distribution has shifted. But notice I keep the green lines the same. Do you know what power is? Power's this little bit up in here that falls above the rejection region if the alternative is true. Yes?
When you're doing these power calculations, and you're asking someone to go to the literature and say, you know, what are other people using, right?
Mm-hmm.
These like cut points. Do you also ask them to kind of like hypothesize what the variance in the sample is going to be?
Yep, well, we've got to get there also, which is usually exactly where everybody freezes. All my clinicians are really good at coming to me and saying, Dave, we hit a 5, we make a 5-unit difference, we're rocking and rolling. And I say, and what's the variance? And it's like, Jeremy headlights. Like, what are you talking about? You know what I do? I take that off your back. Remember, everything's an assumption. Why would I build a grid? Because I can say, what if the variance is this? What if the variance is this? What if the variance is this? What if the differences are these? And I can show you the landscape. But yes, you're going to, but I just wanted to get that first concept in, that under the null, there's going to be a distribution in 2 green lines. And as you start imagining, what are my different scenarios under the alternative? All you're doing is you're moving this distribution around. And as you move it, let me ask you this. Suppose instead of hypothesizing, on this one, I hypothesize that it's a 2-unit, about a 2-unit. Well, you gotta understand I've standardized it here. But what happens if I start making a bigger difference? Suppose you go from, I'm gonna have 2.5, David, let's go to 4. What's gonna happen? No, before you do anything, just say, what's gonna happen? Well, if he moves to 4, the lines stay the same, but he keeps pushing the red distribution toward the right. So more and more of the area under the curve will be above the rejection region. What am I doing to power? I'm increasing it. So as you imagine, if you start thinking about bigger effects, then you would have greater power. The other thing that you could do, so let's go ahead. The main thing is to keep in mind, in your mind, there's a rejection region. As we hypothesize what's going on in the alternative, all he's doing is calculating how much falls above a certain threshold. What's the area under the curve? That's it. Okay, so let's go here. So let's do a calculation. Let's just assume to begin with that the common standard deviation is 5. That's your variance. Okay, I need a standard deviation. Suppose we have a low risk situation. We're just going to use an alpha of 0.05, and that the researcher at most can afford 30 per group. That's why they come. They come to me and tell me that. Okay. Okay. Well, be careful. One of the things I would do, walk everywhere with this. You know why? Because there's software on it. Department pays 10 grand for a perpetual license for the top end power calculation software, and we use it. You can go out there, you can find power calculators on the internet. Don't use them. You can use them to explore what's going on, but sit down, talk to somebody, because some of them actually have errors in them. I hate to burst your bubble, but everything on the internet's correct. Okay? But we can do this, and this worked out in this one. Enter the information. The difference between is bless you twice. 2.5. That's the delta. The sigma is 5, alpha, 0.05. And then we just say, all right, 30. It's just a matter of, it always boils down to there are 4 unknowns. Solve for the 5th. That's it. You gotta, you declare there are 5 unknowns in the power calculation. You assume 4 of them, solve for the 5th. You can pick whichever one you like. They're all, and manipulate the set of manipulate the equation. This gives you a power of 0.4779. That's yeah, I agree. It's low. It's low. And let me ask you something. Told you last week that I'm in my 23rd year of having a PhD. I'm surprised I haven't come to take it back yet. But what is a reasonable level of power?
80%.
All right, as I came out of graduate school, I designed everything at 80% power. I designed nothing at 80% power. Nothing. I actually squeezed it up toward 85. Why? Insurance. That way, if you're off, if either you or I are off in our assumptions, then there's wiggle room, and we stay. We have some problem. So I would ask a statistician first, not calculate at 80% power, calculate at 85% power. It's usually not that much more. And yet you've got a little bit of buffer, and refuse there. So 48% chance. What does that mean? It means if there is truly a standard deviation of 0.05, we use a type 1 error of 0.05. Okay? And we have 30 people per group, and you have created a 2.5 difference in BMI after a 6-week period, you have less than a 50% chance of being able to say, I got a p-value less than 0.05. So do what you got. Or that I have the ability to reject the null hypothesis. Now, I got a little bit of a luck when I said the p-value. The rejection region approach, the one reason that everybody did that is we all know that if the p-value is less than 0.05, you're inside the rejection region. They're 1-to-1, okay? But it's easier to see these graphs and understand if I had to shade, where's the number coming from? It's the region above the green line. In the alternative, that is your power. All right. How would I write it? See, the calculation itself is easy. What NIH is looking for, and I don't mean this bad, they're looking to see if there is evidence and fingerprints of you having talked to a methodologist and worked as a team. I look when I'm at study section, I can tell you when the clinician wrote it or when an epidemiologist or a statistician or a methodologist wrote it. Because if a clinician writes it, the assumptions are missing. We have 80% power. Yay! The statistician writes it, you get this long drawn out. You know what I'm doing? I'm actually providing anybody who understands the concept the opportunity to check my calculation. That's what they're looking for now. Assuming a two-tailed hypothesis using a type 1 error rate, 0.05, common standard deviation, then a total sample size provides 47.79% power. It's exactly the difference between two groups, means of 30 and 27.5. I would tailor that specifically to your outcomes. I would start putting units in. I would describe your experiment. But without all that, that's the bare bones. But if I handed that paragraph to somebody, they have every piece there. Nothing is missing to allow them to run. And all of us know that less than 30% power is not a good situation. What do you want to do? Well, what should we do? How do we move it toward, what levers do we have to increase our power? We could increase the sample size. What else could we do? We could increase the difference. What else could we do? We could decrease the variance. Decrease our assumption on the standard deviation. Make it tighter. Make it less noisy. Tighten the microscope. But all of these begin with the magic word, assume. And you know the old Benny Hill joke? Do you? Do you know what you make out of you do know. Later today, take the word assume and write it down. Put dashes. After the second S, put a dash. Then after the U, put a dash. And it spells a sentence for you. You make a blank out of you and me when you assume. And we need to make our assumptions as careful as we can, but they are still assumptions. And the danger is you have a lot of ability to move a power calculation. I've had people come to me and say, cut the variance in half. I'm like, I can't cut the variance in half without you telling me how you're going to achieve that. What are you going to do? Can you alter variances? Yes, you can alter variances in all processes. That's why the Japanese revolutionized making, now I'm going to date myself, VCRs. VCR was an American invention. It went to market. It was so unreliable, people stopped buying them. Sony got it, figured out how to standardize the process and make less variability in the product, so it was very reliable, sold like phenomenal. Same idea with regard to automobiles. Deming changed everything for automobiles. He was an American. Ford, GM wouldn't listen to him. He said, you got to get the variability out of your process. There are ways to actually engineer, process, and experiment to decrease variance, to increase precision. I'm fine with that, but you got to tell me how you're going to do it. So let's go with this. Let's say I come back and say, you definitely want the 80% power. Okay. I didn't change any. Where did I make my change? I made my change right here. If you're going to make it an 80% power calculation, the delta cannot be 2.5. You got to move it up to pretty much 3.7. If that's under those assumptions, the minimum detectable difference, I'm not saying clinical, the minimum detectable difference with 80% power is 3.7. It's just a calculation, folks. Okay? So like I said, 5 things, assume 4, move the last. What did I do? I assumed, you came to me and you said, David, use 0.05, use 5, give me 80, use 60. I solved the equation, 3.7. That easy. There's the other avenue. You can come back and say, no, David, I want 2.5. I have to have 2.5. Fine. Okay. All right. Now we'll fix 2.5. I won't move that. I'll keep the alpha. I'll keep the standard deviation. I'll keep the 80. But what has to move? The sample size. Now you need 128. That's how many you're going to need. You're going to need 64 per group if you're going to go with that combination. And you see, I'm setting up all these possibilities. And dadgummit, it could be very confusing to keep up with all these. Yes, it could. Let's go on to proportions. Okay, proportions are a different game. A lot of people like to use proportions because it gets around that variance issue. People do not like talking to me about variance or going to the literature. The reason proportions are used so often at times is because I don't need you to quote a variance. You tell me that the probability that 50% of the population is walking around with this enzyme, I know the variance of that distribution immediately. It's restricted by theory. I know what it has to be. You give me a proportion out of a binomial distribution, I know both the mean and the variance of that point. So it's a known fact. It's easier. So everybody says, I'm going to do this. I'm just going to go with proportions. Don't do it. Sample sizes are massive. There's a price to pay. They come. Power calculations are easier through the statistical theory, what I just explained to you. You give me one, that's all I need. I can work it out from there. But also provides all the information for the standard deviations. So let's go back to this game again. Exact same game. Suppose that you're going to have a 20% response rate in both groups. We're having response rates now. David, I would like to increase the response rate by this effect or this magnitude. Now you have all helped me define a distribution under the alternative. So I can start drawing these shapes and considering how much fall of the probability distribution is within the rejection region. 80% power, 0.05, that's 588 people to get a relative risk of 1.5. That's optimistic. If I move that, if you came to me and said, David, we're going to start at 0.5 and 0.5, and we're going 0.5 to 0.6, it's going to be astronomical. It's going to be very big. Okay? So, all right. Here's the key points. This is what I want to give you. We sit down, we do all this. Trying to keep all this in your head is a lot. But if I gave you this, I think A, study section is going to be completely convinced. It's going to be a great thing to have in your archive when you're getting ready to publish, when discuss, because I'll tell you something interesting. Saturday morning, I woke up, I don't know why I wake up so early, even on Saturdays, rolled over, and there's a review paper from a group that I've been working with in South Carolina. And the ugly issue of statistical power raised its head. But it was a very bizarre comment. You have declared statistical significance. You have found a significant effect. But something is horribly wrong with this. Something has gone wrong. To which I'm like, really? Okay, what? And they say you have detected an effect smaller than you anticipated in your power calculation. Can you explain why? Yeah. There was less variability in the data than we thought there was going to be. We had assumed what we thought was going to be we were trying to be conservative. So to be conservative, we made the variance estimate bigger than what might occur. And that's exactly what came down. But I'm able to go back and pull the power calculation and pull the grid to say, look, we know this. So look here, this is what I do. Across the top, these are the difference of means. Let's just hold and study one row. Let's start with 5. See the sigma? Sigma 5, that's my estimate of variability. What happens as the magnitude of the hypothesized difference increases? Does it behave the way you would expect it to behave? Yes, it does. The bigger the difference, the more you're shoving that distribution to the right. So you see that it steadily grows. Okay? What happens as standard deviation increases? Let's stay in the 3.5 column. What's your consequence? You know, as your experiment becomes noisier, power becomes a problem. Because the greater the noise, the more individuals you need to be able to overcome it. So if we go this way, we would expect power to consistently fall. So I would sit with you in a consult and say, look, you're really only kind of safe in these cells. For this sample size, you need to be hoping for these types of combinations. Are they realistic, my dear clinician, yes or no? Okay? If you come to me and say, no, David, I really do believe it's going to be very noisy, I'm going to have to say, well, then we've got to be able to either hope for larger effects and justify that hope in larger effects, or you're going to need to allow me to have a what? Bigger experiment. Yes? You don't have, we're friends. We've known each other for 30 minutes. Oh, raise your hand, it's okay.
I just noticed when you write your table, you put 1 instead of 100, and that's just like statistical, right? It's just like you're not going to put 100% power.
No, I would technically I have gotten. This is a teaching example, but at a point you get to 0.99999. So I mean, technically you cannot get to 100. That's the asymptote. Is the asymptote. Okay, so you're exactly correct. I've actually recorded the asymptote there. I do not like scenarios where I'm showing tables where things are up that high. But, okay. All right, so let's talk about this. We're actually going to get out really early. I'm sorry, mainly because I am not feeling well. Why the most important part of the power section is not the calculation. I do need to check one more thing really quick before I let you do that. Power calculations will be replicated in a few weeks. After spring break. You got spring break next week, right? Yeah, same. We're here. I'm here, but I don't think we meeting next week, or we're not. No, we are not meeting next week. I'm giving you the week. That hurt. But I'll be back the following week. You brought up NIH is really clamming onto this. Actually, they've been doing this for about, I would say, more than 15 years, but they brought the hammer down just a few years ago and said they wanted to see real statistical rigor across the board. Okay? I have sat on study sections for 20 years now for one job. I don't understand any of the biology. I'm relying on all the clinicians in the room to help me understand that. You want to know who reviewer 3 is? Hello. I am reviewer 3, the guy who reviews your stats. And I do my best to give you constructive comments. But it's very, the dean told me I had to stop cussing in front of people. It's very bad for the sprays to be used. There is not sufficient detail in the power calculation to allow replication. That is bad. That means, bottom line, we don't have any reason to believe that you met with anybody. I write that a lot more than you think, but I don't leave it there. I come back around and say, I need to know the following things to allow replication. You did not state a type 1 error. I have assumed 0.05 and tried to replicate it, but I am not seeing the same results. If it was just something that simple, I would say, hey, you accidentally left out your type 1 error. But I found it. I figured it out and let it go. But then most of the time I have to say, most of all, you have not talked about variance and you have not talked about effect sizes. Okay? Even if you do it yourself, again, I don't have ownership of anything. I don't own statistics. I practice statistics. Okay? All of you can understand this concept. You've got it. You can run calculations. You can sketch out a table. But what you probably need the methodologist to do is to make certain you've got the correct numbers through a high-end software. The really complicated designs you will not find on the internet. You will not find the software for that. The other thing is to make certain the explanation is correct. that when it's written up, all the details are there. Okay? All right, and that's it for that exercise. Hang on 1 minute. I want to look at one more thing really quick. All right, well, I do have the second half of it. Never mind. So do y'all want to break real quick, or y'all want me to go on and show you the more complex designs? Y'all want a 5-minute break, or you want to go? Are we saying 5-minute break, yes, or go? Go. Go, David. Okay. Here we go. Okay. Now, we're going to reinforce this really quick. Okay, because this is one of my favorite ones. All right. So still me, same idea. All right. Easy life is too easy. Really? Let me tell you the truth. Sorry, I'm making myself laugh. Really, in graduate school, all they teach biostatisticians to do is a 1 sample power calculation. The easiest example out there. And even in introductory graduate biostats, what we do in teaching everybody else, is the easiest. The second easiest is the 2 sample stuff. I got 2 sample proportions, or I've got a 2 sample t-test. I'm comparing 2 groups. How many people do you think come in with just 2 groups? Clinicians do it a lot. But bench scientists bring me, and I'm not joking. Last weekend, I spent the time building out these power calculators. We got 7 groups here that we're exposing to different compounds. We're putting 3 mice per. Why do you always pick 3? Why do you pick 3? But it was 3 across the board. I will say, if anybody is working in a situation, you would be amazed how much power you will get if you move from 3 to 5. You will be amazed. But I've been beating that drum for a while. So we're going to go to the more fun ones. A chi-square. Why would I use a chi-square? Because I'm not using 2 groups. I'm using 3 groups. Anytime I go beyond 2 groups, if I move from beyond 2 groups, I move from the 2 sample t-test to what? What's the procedure when I have more than 2 groups? You know, in a continuous outcome? What? ANOVA. What does ANOVA stand for? Very good. And what does it test? It tests for differences among 3 what? What? Means. Perfect. It's the classic bait and switch. It's a hypothesis test about means, but we named it the analysis of variance. There's a reason for it. Because if the means are equal, I can create 2 estimators of the variance, and they have to be the same. They have to be close to one another. If the alternative is true, the first estimator of variance will overshoot drastically. The second one will always be correct. So by analyzing 2 estimates of variance, of the same variance, I can deduce whether the means are equal or not by determining if they're close together or not. Okay? We've already talked about this. All right, so here we go. We're going to do ANOVA first. Excuse me. So in this one, the null hypothesis is mu1 equal to mu2 is equal to mu3. Now I've thrown in 3 groups. And the alternative has to be ui not equal to muj. You've got to move at least one of the means out of equality. So now it gets even more complex because I can come up with 2 means that are equal, but 1 is out of place, the third one is moved. I can make all 3 different. We have to walk through all those combinations. Okay? Why do we call us an analysis of variance? Because here's the truth. The basic answer, mu1 equal to mu2, mu3 implies that for those 3 numbers, there is no variance. Think about it. If I tell you the numbers are 27, 27, and 27, what's the variance? 0. It's an analysis of variance. We're asking what's the variance among these. Under the null, there is no variance. I need to come up with an alternative where the three numbers do not equal each other and are contributing variance to the calculations. All right, or contributing calculation to the, or variance to the data. All right, so we're gonna have a thought. First, remember there are two hypotheses. It's the exact same scenario, but in this one, I try to have a little bit more mercy on you. I do not sit here and say, come up with all these. I start working them out and mapping them because some of them are redundant. Okay? I'm going to show you that in just a minute. Please keep in mind, this is the truth. In every power calculation, you're only studying a little piece of the huge map. There's an infinite number of possibilities that we could guess here. Same thing under the two sample. There's an infinite number out there. We're just going to look at a subset and say, in this region, we're very confident, or we've got a high probability that if this difference exists, we will find it, or if this situation exists. Because at this point, it's hard to talk about differences. Which difference are you talking about? Are you talking about the difference between mu1 and mu2? Or mu1 and mu3? Which one are you talking about? So we could assume another possibility. You could assume all three are equal and then 30, 25, 25. That's valid. The alternative, the null is no longer true. I've hypothesized three numbers that don't equal each other. I could do 30, 30, 25. Now, newsflash for you. They're both going to produce the exact same power calculation. Because all that matters is the variance among the numbers. That's all that matters. That's what's driving my calculation. Okay? Now here's where it gets fun. Somebody explain this to me. Yeah, I love that. Do you remember the two bells I showed you? I'm going to give you a hint. The red line is the distribution under the null. Remember something. Not everything is a bell or a normal curve to a statistician. In ANOVA, the correct null distribution is an F distribution, which has this shape. That's what the F looks like. Then we start, and this is the fun thing. You have the F distribution when the null is true. Then you have what's called a non-central F when the alternative is true. It's still an F, but it got warped. It literally warps and starts changing its actual shape. It doesn't shove left or right. It actually warps. But notice the green line is not gonna change. Or here, the blue line does not change. So all this under this little red piece right here, what do you think that piece is? That's my rejection region. How much of the area is in there? Alpha, 0.05. We always draw the line so that we get 5% under the null. That's how the line is anchored. The first curves, I had two lines. Each of them together would have given me 5% under the null. This line, there's a magic 5% sitting. I'm sure Brian loves it when I touch his screen. Under the curve. Now, what do you think for the green curve, which is what the alternative is? What is this shaded region? Say it.
Power.
That's your power. Always remember, you can draw these out and shade them. Now here's the cool thing. As you keep drawing or pulling or creating bigger effect sizes, suppose I don't do 30, 30, 25. Suppose I go 30, 30, 20. It's a bigger effect. What happens is literally you're starting to shove that green curve and it's stacking up like a wave. There's a wave moving through that green curve as you create bigger effects, and you're shoving more of the area above the threshold or above that cut point. And that's creating or estimating your power. Every specific combination will lead to a different green curve that allows me to calculate how much of that curve is above that threshold. That's all power is. It's a bunch of assumptions and a bunch of two figures shaded. Okay. Okay, we have to have a common standard deviation. This time I say 0.05 and assume that, again, assume 0.05. I'm back to that guy who says I can only have 30 per group. Okay, that's fine. Again, we've done everything we need. We have the 5 components. We have our effect size, which you gave me the components that I can work that out mathematically. You gave me an effect size. You give me a standard deviation. You give me a type 1 error rate, or I give you a type 1 error rate. You give me a sample size. I've got 4 assumed. What's the last one? That's the one I calculate for. I'm calculating power. So, what does this map to? Well, it comes to this. This is the way I would write it in a grant application. In a one-way ANOVA study, sample size is of 30 per group. For 3 groups, I have to tell you the number and the number of groups provide 61.6% power to detect differences among hypothesized means of U1, 30, 25, and 20 using an F-test and up to 0.05 significance level. Now, I come in and I add more detail. This is really me putting my fingerprint on your grant to say, a statistician wrote this. The size of variation in the means is represented by the standard deviation, which is 4.08. So that they understand this is, if you really want to replicate it, I'm going to make it very easy for you. Here's the first piece. Here's the effect size statisticians would use instead of reported. But everything is there, okay? All the assumptions listed out. Is that good power? Is that good power? No. What would you do? What are your avenues to increase your power here? Talk to me. Increase the sample size per group.
Larger differences in the main things.
Pardon me?
Larger differences.
Larger differences. Multiple ways to do that. I could take one mean, move it way out. I could take or stack out the means more evenly, but bring them out. What else? Create more variance among your means. What? What else?
Change your alpha.
Change your alpha, which always makes me nervous. Makes me nervous because if you're going to increase your power, what do you have to do to alpha? You don't lower it, you raise it, which is a no-no, and I've had that. I'll use an alpha of 0.10 for pilot studies, and I've had it go through study section, but I was also in a study section where it got super nasty between the methodologist and the clinicians. The clinicians wanted it funded. The statisticians were like, over our dead bodies, because it had a type 1 error rate of 0.2. Alpha of 0.2. And well, I won't go any further. I was not happy that night. We lost. And I really felt like we're going to subject people to an experiment that I don't think I will believe any of the results if this ever gets published. And my comment was, it's never going to get published with an alpha of 0.2. I've never seen a study with alpha 0.2. So here we go. Same grid as before. 15, now notice I've changed the direction. Here, the residual variance or residual standard deviation, which statistician would call the root mean squared error in this situation, is getting smaller. So as we go down, as the variance is twisted down, you would expect the power to go up. And that's what you see. So here, if you can tell me that, if you can find me literature indicating that the residual standard deviation is about between 10 and 5, we're doing great. We're fine. We can adjust this a little bit. Now look at this. Clearly I made a mistake in my table, right? Clearly, David, stop being so sloppy. Is there a mistake in my table? These two rows are identical. Is it a mistake?
It's just because the views are
The views are
like the same, but
kind of hard to say, isn't it?
same but not same. The variance is the same.
The variance among the means is identical. So you've got two sets of means producing the exact same effect. So there should be no difference between these two rows. And that was a key thing. In ANOVA, your effect size is the variance among your hypothesized means. Okay? Because I could have just as easily said, let's do 20, 25, and 30, and that's not going to give you anything different. Same set of numbers, it's the variance. All right? So in this scenario, we can tell you right now, if your root mean squared error is sitting up at 15, I'm not feeling very good. I'm going to have to come report to you that you're going to need to jack up your sample size. Huh?
Like a million.
No, it won't be a million, but it's got to go up. Here we're okay, but nevertheless, the only thing that's reasonable, anywhere close to reasonable in this table, is that top row. And we would have to come back and start reconfiguring our assumptions until we get to something that one thing, please, I like team science. I love teaching. I love team science. I love sitting down and helping people advance their careers. It's been very fun for 23 years. But one of the things that I find very interesting is I need clinicians to be able to be very bold with me and say, David, we can't get that many people. There's no use in me proposing something that you know you can't do. We can keep working until, bottom line, sometimes we've done this before. Somebody's using a psychometric instrument to measure cognitive disability. And they really love this psychometric instrument. It has a standard deviation of 10. We can't get it to fit in their sample size. We keep exceeding the number of people that they think they can get. What's the solution? Change your psychometric instrument. We actually went out and found one that actually had a standard deviation of 5. Now we had to adjust our effect sizes, but that gave us the ability to say we will have more precision. And it was still a valid instrument, so we used it. So just think about those things. Yes?
When you're proposing these tables, do you ever include these? You've showed us a lot of paragraphs that you include in NIH proposals. Do you ever put this table? And if you
I put that table in there and I picked one specific row to explain.
Okay.
And then follow it with 2 more sentences to help them say, if our initial assumption of this standard deviation is incorrect and we have greater variability, we still maintain at least 80% power up to this threshold.
And do you then have the researchers cite some sort of literature to say that the row you highlighted is,
Yes, that's exactly what I try to do. And if we can get all of that, that's the strongest calculation. Yep. If you can't say specifically, I will say we can cite these types of standard deviations. We proposed the consideration of ranges around it to recognize that our chances of having the exact same standard deviations are mathematically 0. I won't put it that way. That'll sound like a geek. Yeah, go ahead.
What part of the equation changes when you have a paired sample design?
Oh, great question. Great. Now, let's ask us the question. Now, you've got a paired design. How many groups are you doing? Is it just one group where you say we're going to do pre on all these individuals and then move to post? we're back to a one sample hypothesis test and we're under the t-distribution. So we're back to the bells. Okay, if you are doing dichotomy, you have urinary incontinence before your gastric bypass surgery, and then 6 months after, we test to see if you still have urinary incontinence. I did this study. It's amazing how much the decrease was. Really, honestly, I was surprised. That's a chi-square. So that's why you come to a statistician. You can do paired observations on binary outcomes, but it's a special test called McNamara. But it maps to the chi-square, which would map us to two specific shapes, one for the null and one for the alternative. Same principle though. As you hypothesize bigger difference, you're literally creating almost like a tidal wave in that alternative distribution. You're shoving it, and more of it is falling above your threshold, which increases your at least allows you to visually understand what the power calculation is doing. Okay? So that's why you should come to bird clinics, because you can sit around for hours and have a free lunch. Today we have free lunch from 11:30 to what? 1. And we can talk stats all day, and you can eat lunch off of us. And we can work out your power calculations. But that's why, part of the PhD in methodology is to know, I got a paired design, McNamara's, paired t-test, repeated measures ANOVA. Which one am I doing? You can do, remember paired, you can do more than 2 observations. You could measure the person at baseline, 3 months, 6 months. I designed that last night. How do you analyze that? So just to come and talk to a methodologist, and we have all of the different scenarios mapped to power. So, all right. So we could do the bottom line. Suppose you have a more complicated, possibly you got 2 treatments. No reason you don't have 2 treatments. I mean, I do this design all the time. Drug alone. All right, well, first, we randomize you to behavioral or no behavioral intervention. Simultaneously, we randomize you to drug, no drug. All of a sudden, I got 4 cells. You got nothing. You're the control arm. Congratulations, we're not telling you that. You're the behavior-only arm. You're the drug-only arm. And then you get the combination. Everything stays the same. There is nothing different. The only thing that's different now is in this scenario where we've got treatment 1, which has 3 levels, and treatment 2 that has 2 levels. Now you're hypothesizing how many means? 6 means. And there's many ways you can change it. You could put all of these guys equal, but make this row different, and all of these are equal. And that would have created variance, but that would have told you that treatment A has an effect, but treatment 1 has no effect. You could do, these are equal, and these are equal. If you do that, what you're telling me is treatment 2 has no effect, but treatment 1 is the driver. Or you can make it really complex and say, test them all. And I can. And under this scenario, I don't hand you 1 power calculation. I hand you 3. I test whether treatment 1 has an effect, whether treatment 2 has an effect, and then whether there's a synergy or an interaction between treatment 1 and treatment 2. So that you understand, statisticians use the term interaction for that. Do you know what that test is? All that term means is I'm asking, is the gap here, is the difference here equal to the difference here, equal to the difference here? That's all the test is. That's the null hypothesis, that these are all equally spaced apart. But if they're not equally spaced apart, that means the impact of A or B is dependent upon which column you fell in. And that's an indication of synergy. That's an indication of interaction. I stay awake at night trying to figure out how to power interaction test. It's very hard. It's very hard. Okay? It's very hard to explain also.
To properly power a study where you think the interaction is
The
the
driver
driver.
is going to be a very large, I have papers out there talking about what assumptions make it easy, which ones make it much harder. But a test of interaction is often underpowered in most experiments.
But generally that interactive effect, biologically speaking, is the most interesting.
I know. I know.
Sorry.
No, don't be sorry about it. If it wasn't a problem, I wouldn't have published stats papers on it. So I'm going to keep us going. I'm going to let you go in 5 minutes. When the outcome is dichotomous, proportions are your outcomes. It's the exact same idea. Now I got to come in and say pi 1 is equal to pi 2 is equal to pi 3. There's no variance there, folks. No variance. The null hypothesis is true. There's no variance among the probabilities. But here I could say maybe the response rate is 20% in group 1, 30% in group 2, and 40% in group 3. So that I see them spread out. Again, once I've got all that, notice I don't have a standard deviation up there. I don't need standard deviations when I'm playing with proportions. Stats theory hands it all to me. 0.05, that total sample size is 306 individuals to get us to 80% power. Okay? Again, it always boils down. Do not forget, what are the magic 5? I need, let's take the easy one, type 1 error rate. I need an effect size. Sometimes the effect size helps me get the standard deviation. If I don't have that, I need the standard deviation. Then I need sample size and I solve for power. But if you say, David, I want you to give me a sample size calculation, you come to me and you say, this is my effect size, this is my standard deviation. David, is 0.05 okay? Yes. Then you come to me and say, and I want 85% power, then I produce the sample size calculation. Okay? And that's the way it works. All right, and here's the other game again, okay? Same thing. This is one way I do it. This is a different table than before. Look what I've given you here. I've actually now just said, and this is a good table to have in clinical experiments. You know what the biggest problem with clinical experiments are? Finding people. Not calculating power. It's, you got it funded, now you're recruiting, and all these people that you thought would be there, have actually disappeared. So this is saying, this is a good table to have, because I'll put up here projected sample sizes. Because even though I say I'm going to go get 240, I might run out of clock, and I stop the study with 220. What's the impact? Now, in this scenario, that's a bad scenario. You see that dropping by 30 individuals has dropped you down to the 75% power. If you missed it really bad and we're down at 240, you're all the way down to 70% power. If this is what you've hypothesized. Why are the rows so much different? What happened? Talk to me before I dismiss you. Why is power lower on row 2?
Lower variance.
Thank you. There's less spread among the proportions hypothesized under the alternative. The more spread out, the bigger the effect, the bigger the power. The more tight, the less variance for a fixed sample size, lower power. Okay. All right. And you've already heard this, and that's it. And, ooh,